Okay, applying graph transformations to trigonometric functions. Now in Math 135, you learned some basic um, transformations and what it does to the function. So for example, changing y to y plus a, you move it up or down. Changing y to y minus a, well, y plus a moves it up, y minus a moves it down. Changing x to x plus a moves it left, moves it right. Changing a function to its negative is going to be reflection, and so on. Right. Now, the simplest way to look at that is, let's say you consider y equals x. That's a line that goes through the origin. Now, if I change this to y equals x minus 1, this would move to the right. Yeah. If I change it to y equals x plus 1, it moves to the left. Now, y equals x plus 1 is also y minus 1 equals x. Right? And y equals x minus 1 is also y plus 1 equals x. So maybe adding plus moves it down and a negative moves it up. And changing this to negative x makes it flip, so it's a reflection. So these were transformations that you've learned. Now in case of, for trigonometric functions, you can obviously apply these transformations, but there are other kinds of transformations which are specific to periodic functions. So the two particular transformation with respect to sine cosine is you take the function and you multiply it by a number, and you take the function and you multiply the input by. So here the key difference is you multiply the output, and here you multiply the input. So you're trying to see how the function changes when you multiply the output, and then you're also trying to see how the function changes if you multiply the input. Let's start with a simple graph of y equals sine x. Now we've seen that the time period is 2 pi, the max value is 1, the min value is negative 1. Now for these trig functions, there are two fundamental values we talk about: amplitude and time period. This amplitude is the max value, and the time period is when it starts repeating. So here the max value is 1, so amplitude is 1. We use A to denote amplitude, and the time period is 2 pi. Let's just call it time period, because after 2 pi this graph is going to repeat. So that's what the sine function is going to look like. It repeats both in the positive and in the negative direction. So we're going to look at this first case. What happens if I multiply the output? So for example, what happens if y equals 2 sine x? So what happens is you still get the same structure, but now you multiply the max and the min value by 2. So the amplitude is 2 and the time period is the same. This was the original function, and you multiplied it by 2. So it still meets at the same points, reaches 0, but it just is going to be bigger. So you can generalize for varying values of k. What's going to happen is, if this is sine x, this is going to be sine 2x, this is going to be sine 3x, and this is going to be sine, or 1/2 sine x, this is going to be, say, 1/3 sine x, this is going to be negative sine x. Right? So because you can also multiply by negative numbers. This is going to be negative 2 sine x. So what you get is you get this whole range of graphs for various values of k. So multiplying the output, what does it do? it changes only the amplitude. Okay, so it just changes how big or how small, not small, but how low or how high the sine curve can go. So that's how you mess around with the amplitude. Now, since there are, again, since we established two fundamental properties, amplitude and time period, and we saw that there are two ways in which we can transform these functions. So the next goal is to see how to play around with time period, and obviously that happens when we mess with the input. Okay, so let's first compare it to sine x. Okay, let's say this is sine x. Sine x behaves exactly like that. This is 2 pi. Now, what is really happening when I double the input? Right? Let's see. Now, in sine x, when this input is 2 pi, I have 0. But if my function is sine 2x, I get to 2 pi when x is pi. Right? So if I have pi here, this 2 pi actually maps to pi. Similarly, I get the input is pi here when x is pi over 2. So pi actually maps to pi over 2. So by symmetry, what is happening here is that we say that this entire graph is getting squished into the smaller graph which ends up at pi. But it still is a sine function, and since there is no number in front, its amplitude is still 1. All we are doing is we're sort of squishing it. Okay. So what we're saying is, another way to think about it is that when you make it sine 2x, you make the graph travel twice as fast. So the whole thing gets squished into, and so the time period now has changed. Because the 2 pi is getting mapped to pi, the time period is pi. Whereas the amplitude remains the same at 1. Okay, let's look at some examples and how do we plot them. So 2 plus cosine x. So let's start with cosine x, right? And that's cosine x right there. 2 pi 0. 2 plus is adding 2 to the output. So I add 2 to this. So my max value is now going to go from 1 to 3, and negative 1 is going to stop at 1. Right? So this is going to be 1 and this is going to be 3. Negative cosine x. I start with cosine x, 2 pi. Negative cosine x means I just flip it on x-axis, like flip. Because now these positive values correspond to negative and these negative values correspond to positive. So that's going to be negative cosine x. Negative 3 sine x. So here I'm going to go from cosine x to 3 cosine x and then to negative 3 cosine x. What does that imply? Cosine x, 3 cosine x only changes my amplitude, so it's just going to start at 3 and be at negative 3, and then adding the negative simply flips it so that this is negative 3 and this is 3. 1/2 sine x, so I start with sine and I just make it smaller, right? The amplitude is the same. This is 1/2, this is negative 1/2. This was 1, this is negative 1. Let's look at this one. So here I'm going to start from sine x. I'm going to change sine x to sine x over 2 and then negative sine x over 2. Sine x looks like that. Now instead of 2x, this is x over 2, which means this graph is going to move slower. So this is actually going to go to 4 pi. And then making it negative just flips it around, so that this is -1, this is +1, and the time period remains 4 pi. Now you can even be doing both the things, right? For example, 4 cosine 2x. This means you go from cosine x to cosine 2x to 4 cosine 2x. So you start with the plot for cosine x. That's just regular. This is 1 and the time period is 2 pi. 2x makes it twice as fast, so everything is condensed into pi, but the amplitude hasn't changed. But then going to 4 makes the amplitude 4, but the time period is still pi, because the 2x caused it to squish down to pi. So whenever you're plotting with these transformations, just go step by step, do one transformation at a time to get to the final result. Okay. In the next video, I'm going to put all of these together to see all possible transformations that can be made for a trig function.